our objective for this lesson is to know the basics of exponential functions. So we're going to look at not only the formulas, but the graphs and then applications of it so we know the overview of what we're doing. So first of all, we're going to look at the basic formulas for these. What you have to recognize for an exponential equation is that the variable is going to move up to the exponent. So we've got a new type of family of functions that the variable is going to be in the exponent. So when we look at the general form for a basic formula, it looks like this: y equals a times b to the x power, where this a is equal to the initial value. So if we're talking about an application, it's where we start the whole problem. And the the b here, we call the base just because it's going to be what tells us is going to be the growth factor, or if it goes down, the decay factor. Now, the next part, if we're going to do a complex formula for this is if we're going to move it side to side or up and down. So the look of this formula will be y equals the same initial value times b, and we're going to use the same notation we've used with other families of functions. We're going to have x minus h up here in the exponent. And then secondly, we're going to put down on the regular level a plus k. Now this minus h, this moves it horizontally. Okay, so side to side, and this k moves it vertically. All right, so we have to recognize that this is what we're going to be looking at, and then if we start adding or subtracting numbers, that's going to move it around. Now, a basic idea that I'm going to put up here in this will help you for the whole chapter on exponential functions. We have to recognize that 100%, that's just the number 1. So when we do these problems and you see the number 1, it represents 100%. 1 times something is itself, so it's 100% of itself. But we got to recognize that because we're used to 100% having a couple zeros in there, but when you change a percentage to a decimal, you move it over 2 places, so it becomes just the number 1. You'll see that reflected in several of the problems and the work we do. So let's look at what the basic graph looks for each of these. The 2 things we're going to look at is growth and decay. Growth is when the value goes up, so the base value will be above 100%, and the decay will be when the value goes down. That's when the base value is going to be less than 100%. Like for instance, 0.75 would be a base value that would have the value decay. So if we look at the basic graph of a growth function, it does have an asymptote, but not over on this side. So when you look at this graph, the asymptote is going to be the x-axis for the basic look of the problem, but it's going to keep going as wide as we need it to. So it's not like our rational functions where it had a vertical asymptote here. It keeps going. So this would be if b is greater than 1. So here our base would be greater than 1, more than 100%. So our growth factor would be 1 plus r, r being the rate. So if you have, like for instance, a rate of growth of 6%, 1 plus 6% would be 1.06. A decay factor would look like this graph. It would start high and then go down to have an asymptote at the axis. This is when our b is between 0 and 1. All right, now neither one of them equals 1. If it was just 1, it would just be a constant graph because we'd have 1 to the x power. It would just be multiplying by 1. So on this one, this has a decay factor of 1 minus r. So you subtract, like if it's going down 6%, 1 minus 6% would be 0.94, 100% minus 6%. All right, let's look at the equations for these. So generally our equation for this, for both of them, is going to be y equals a times b to the x power. And it's going to be the same thing here. This would be b is greater than 1, so we'll just remember that same thing. This is the same equation of the basic equation. This would be just where b is between 0 and 1 for it. Now, when we do key features, it's going to be the same for both of them. The domain for these is going to be all reals. The range, now we have to know that this is for the, when we're talking about the basic one, this is going to be y is greater than 0. This is just for the basic, okay? If we were to do, the complex, then that might move it up or down. So we want to make sure we realize the complex, what we would have is that we'd have y is greater than k, or we could be able to flip it over if we have a negative coefficient in front, if our initial value is negative. So that's something to keep in mind, all right? For our intercept, this is again the basic one. So we'll use for the basic, it's going to be 0, a, the initial value. And for our asymptote, that's the y-axis. Okay, so this is all for the basic values. It changes, these can change for the complex if we move it up and down, etc. All right, so let's do end behavior. End behavior for this, what we're going to do is as x goes to negative infinity, our y is going to go to up to 0. It's got, notice on our graph here, our y goes to 0 here, whereas it was x goes to positive infinity, y is also going to go to positive infinity. So as x goes to positive infinity, y goes to infinity. That's for the growth one. Now for decay, it's going to be as x goes to negative infinity, the y is going to go to infinity. Notice that on this graph, as we go to negative infinity, the y is going up to infinity. And then as x goes to positive infinity, the y is going to go to 0. It's going to go to that asymptote. All right, so the models, and this will be for the application, this is when we're going to go with growth and decay. The basic formulas we're going to use will sometimes look kind of like this. We'll either use a of t, t being for time, okay, or we might just use a equals, so it will vary, but if we use it in function notation, a of t equals the initial value times 1 plus the rate of growth, so 100% plus the rate would give us a decimal for that, and that's to the t power. So the variable here will be time, and for decay, that's going to be a of t equals a times 1 minus, you subtract the rate here, so minus r to the t power. So that's a summary of what our growth and decay are going to look like. So here's an application idea to it, just so that we kind of get a feel for what this looks like. So when we do the application here, the general formula for growth, as we just said here, I'm going to list it here as a of t, t being time. So we've got t is time, a is the initial amount, r is the percentage of rate of increase or decrease. So it's going to be a times 1 plus the rate of increase to the t power. So as an example here, if I were to do this problem, I'd have a of t would equal the initial amount 50 times 1 and then plus the rate. Now make sure you don't put 7, you put 0.07 because you've got to turn it into a number without the percentage on it, and that's to the t power. And let's just rewrite that then, 50 times 1.07 to the t power. So you see this base is greater than 1, so it's going to make it increase. Whereas decay, that's when we subtract the rate, 1 minus r to the t power. So when we do a problem like this, we're going to have a of t equal to the initial amount 30 times 1 minus 0.20. When you subtract the 20%, you move the decimal over 2 places. That's minus 0.20. So if we lose 20%, that means we're going to be down to 80%. So we're going to have 0.80 to the t power. So that would be a decay problem, a decrease, whereas this is an increase because it's greater than 1. All right, so that summarizes how we get to some of the basics of the problems and then also how to do applications. Let's go ahead and look at some of our graphs for these. And I'm going to do just show you how these graphs start and end. Notice that these will sometimes move around, sometimes they won't. All I'm looking for is, if I'm looking here, notice that this 3 means that it's going to be an increase because that's the base that has the exponent. I have no a times it out in front of it. Down here, notice here I've got a 2 times the base to a power, so that's going to be the initial amount 2. But here, when I do this problem, okay, I'm going to have my initial amount be 1, but then I'm going to add 4 to it, so that moves the initial amount up. So when I do this, this will mean that this will be my asymptote. So whatever number you have out there, originally the asymptote would be at the x-axis, but since we're moving it up, that's what the plus 4 does. I'm going to have up here at 4 an asymptote. And so my graph will start out there, and so it will go through an initial amount at 5 because it's 1 for this part. If I put in 0, I get 3 to the 0 is 1, and then I get 1 plus 4 starts me at 5, so the initial amount here would be equal to 5. And I'll just put down the original 1 plus the 4 gives me 5. And then it goes up from there if you were to put in values. And so it goes, the graph will look like this. Okay, near the asymptote, but it does get wider. It doesn't have a vertical asymptote. Okay, the domain for this, domain for all of these is going to be all reals. So from negative infinity to infinity. The range will be, notice that we don't actually get to the 4, so the lowest is 4, so we're going to have an open parentheses on 4 and then go off to infinity for my range. Okay, so let's go ahead and do the next one. Notice that this one doesn't have a vertical or horizontal shift, so it's going to stay here down by the axis. So because I'll put a plus 0 here, there's no number out here, so 0 is my asymptote. So you just look for what's being added or subtracted out there. So just keep the asymptote here at the axis. Then when I go ahead and put in values, if you were to put this in your calculator and get values, it would go through an initial amount of 1 because there's no shift. So initial amount equals 1. So you could do a table. Your calculator will give you a table for this. And so I'm going to have at negative 1, it will be up at 3. And over here it will be down close to the axis. And so my graph looks like this. Now notice that's a decay problem because this number, the base, is less than 1, so it's going to decay. All right, this one we're going to have decay because it has a 1/3 there. It's going to move the initial amount up by a factor of 2, but then also it's going to move it down 6 units. So this is going to have an asymptote at -6. So down here, 1, 2, 3, 4, 5, 6. -6 is an asymptote down at the bottom. It's now going to have, if you look at this x plus 4, it moves my starting point -4 units and then down 6 down here. So if I were to do a table off my calculator here, okay, I'd want to have a 2 minus 6 would give me a -4 for a point, and then this point here, remember you go opposites, so it's going to be a -4 for that one. And then if I get values off of my calculator, here are some other ones. So it's been shifted 4 units over and 6 units down. And then I get some other values like -3, I get -5.3. Okay, and so for this, I'm going to start my graph over here. -4, 1, 2, 3, 4, 1, 2, 3, 4. This is kind of that initial starting point, but it's been moved over. I'm going to have -5, 0, and -6 will be way up at 12. So it's going to come down very quickly, and then it's going to go -3, 1, 2, 3 will be at let's see, 5.3, so right about there. So it's going to come down and be close to the axis. My domain for this one will be all real numbers, and my range will be, notice that it never gets to -6, so the lowest it gets is -6, and then it goes off to infinity from there. Okay. So when we look at these graphs, we look to see how these numbers impact moving it side to side or initial values, and then we look for our domain. Like the domain for this one is all reals, so it goes from -infinity to infinity, and the range for this one, the lowest it gets is to 0, so it goes 0 up to infinity. So you just look for your asymptote to tell you how low it goes. That's the number out at the end. Sometimes it shows up. If it doesn't, it's a 0. So look for these basic ideas of where you start your graph. Use your graphing calculator to help you out, but get a sense of how these numbers interact with the graph to move it side to side, and then also stretch it up or shrink it down.